In section 2.3, we look at solving right triangles. Before we solve right triangles, we need to talk about significant digits. So anytime you measure something and you write down that measurement has what's called significant digits. The definition is the number of significant digits in a number is found by counting the number of digits from left to right, beginning with the first non-zero digit on the left. If the number in question does not contain a decimal point, then trailing zeros are not significant. So as an example here, we would like to give the number of significant digits in each of these measurements. So in the first triangle, we see that this side has a measure of 0.042. So according to the definition, we start counting with the first non-zero digit on the left, which is this number right here. And then we just count to the end of the number. So this number has 2 significant digits. The next number, 20.5, if we start counting the first non-zero digit on the left, this number has 1, 2, 3 significant digits. The next number, 6.000, since it has a decimal point, we will count the first non-zero digit on the left and count all digits to the end. So this one has 4 significant digits. The final number does not have a decimal point. So if we start counting with the first non-zero digit and we don't count the trailing zeros, this has 1 significant digit. Now, if we wanted the 700 to be significant, all 3 digits to be significant, the way we would write that is 700 with a decimal point and then no zero after the decimal point. If we wrote it that way, it would have 3 significant digits. When solving right triangles, we need to make sure that the accuracy of the measurement of the sides agrees with the accuracy of the measurement of the angles. When we measure the sides to 2 significant digits of accuracy, we should measure the angle to the nearest whole degree. When we have 3 significant digits of accuracy on the sides, we should measure the angle either to the nearest 10 minutes or to the nearest 1/10 of a degree. If we have 4 significant digits for the sides, we measure to the nearest minute or the nearest 100th of a degree. So in the second example, it says for each triangle, round the number in parentheses so that its accuracy corresponds to the accuracy of the other numbers in the triangle. So I want you to notice in the first example here that the measure of the side here is 2.3. That has 2 significant digits, and 2 significant digits means that the angle should be measured to the nearest whole degree, which is what we have here. So now we need to correct the measurement of this side. This side should also be measured to 2 significant digits. Right now, this number has 4 significant digits. So if we make it 2 significant digits, we're going to cut off that number at the second decimal place. And if we round that, we get 0.94. In the next example, notice that the side has a measurement of 197. That is 3 significant digits. And the angle is measured to the nearest 10 minutes. And that's consistent with our guidelines up here. So now we need to measure this side here to 3 significant digits, just like the other side. So 3 significant digits would be these 3 digits here. If we cut that off and round the result, we get 887. And in the final example, notice that both of the sides are measured to 4 significant digits. And if that's the case, the angle should be measured to the nearest 100th of a degree. Well, this angle is measured to the nearest 1,000th of a degree. So we should be cutting off this measurement to the hundredths place. And if we do that, we get 40.28 degrees. So what we're really doing there is we're just dropping the 0. Now let's talk about solving triangles. In this section, we only look at solving right triangles. We only have the tools at this point to solve triangles that have a right angle. Later on in the course, we will learn how to solve all different types of triangles. Now, when we say to solve a triangle, what we mean is to find all the missing sides and angles of that triangle. And when we're talking about triangle ABC, we will always assume that angle C is our right angle. So in this example, it says in right triangle ABC, angle A is 40 degrees, side C is 12 centimeters. We want to find side A, side B, and angle B. Again, we're assuming that angle C is the right angle, 90 degrees. We know that side C is opposite angle C, and then angles A and B are the other acute angles in the triangle. Angle A is 40 degrees, so over here we have side A. Angle B is here, and so over here we have side B. Now to solve this triangle, I'll do the easiest thing first, which is to find the missing angle. In this case, the missing angle is angle B, and we know that angle B is complementary with angle A. And so that means that B should be 90 degrees minus 40 degrees, which is 50 degrees. Now, to find the missing sides, let's go ahead and start with side A. Notice that side A is opposite the given angle, which was 40 degrees, and the other side that we know is 12. So we have an angle 40, we have the opposite side, and then we have the hypotenuse. That relationship is the sine relationship. So we know that sine of 40 degrees is equal to the opposite side A divided by the hypotenuse 12. To solve this for A, we're going to multiply both sides by 12, and that allows us to cancel the 12 on both sides. From there, we get A is equal to 12 times the sine of 40 degrees, and if we plug that into a calculator, this calculation gives us 7.713451316. Now, this is an extremely high degree of accuracy, which really doesn't make sense given the fact that we only measured the hypotenuse to an accuracy of 2 significant digits. So we should measure this side with the same degree of accuracy, which means we need to measure this to 2 significant digits. If we round this number to 2 significant digits, we get 7.7, and this should be in centimeters. Now to find side B, we essentially do the same thing, except that side B is the adjacent side to the angle 40 degrees, and then we have the hypotenuse 12. So when you look at the adjacent and the hypotenuse, that relationship is described by cosine. So cosine of 40 degrees is the adjacent side B divided by the hypotenuse 12. If we multiply both sides by 12, we can cancel the 12 here, and we end up getting B is equal to 12 times the cosine of 40 degrees. And if we plug that into a calculator, we get 9.192533317. And again, this is an extremely high degree of accuracy. We don't have any reason to expect that our answer is this accurate. So once again, we should cut off our measurement to only have 2 significant digits. So 9.19, when rounded to 2 significant digits, is 9.2 centimeters. So now I'll just summarize the solution to this triangle. I like to put the solution in a little box like this. Angle B is 50 degrees. Side A was 7.7 centimeters and side B was 9.2 centimeters. In this example, we have right triangle ABC with side A being 2.73 and side B 3.41. We want to find the remaining sides and angles. So first, we know we can use the Pythagorean theorem to find side C. We know that A squared plus B squared is equal to C squared. And we know that side A is 3.41 and side B is 2.73. And when we square those and add them together, we get 19.081 is equal to C squared. To solve for C, we take the square root of both sides, and the square root of C squared is C, and the square root of 19.081 is 4.36818, etc. So we'll round that to give C is approximately equal to 4.37. That's 3 significant digits of accuracy. Now let's find the angles. To find angle A, notice that for angle A, 2.73 is the opposite side and 3.41 is the adjacent side. So from there we have tangent of angle A is 2.73 divided by 3.41. Taking the inverse tangent of both sides of the equation gives us A is equal to the inverse tangent of 2.73 over 3.41. Let's plug that into a calculator, and once again, make sure that your calculator is in degree mode when you do this. And when you do that, you should get 38.68, etc. degrees. And rounding that to the nearest tenth of a degree, we get angle A is approximately 38.7 degrees. Once we have angle A, we can find angle B by simply taking the complement of angle A. And when we do that, we get B is approximately equal to 51.3 degrees. So we have our solution box here. We found side C to be approximately 4.37. Angle A is approximately 38.7 degrees. And angle B is approximately 51.3 degrees. In the next example, we are given a circle, and the center of our circle is at the point C, and it tells us that the radius is 21 inches. This angle A outside the circle is 41 degrees, and we want to find Y and then find X. Now in geometry, we learned that when we have a point on a circle and a line tangent to the circle at that point, which means that it simply touches this point, or the circle rather, in one point, we learned that the angle here has to be 90 degrees. Now they don't say that, they don't show you that in the diagram, but that is a geometric fact. And also the angle on the other side here is 90 degrees. So I just want you to notice that we do have a couple of right triangles. Now they tell us that the radius is 21. So R here we can say is 21. This R over here is also 21. And then angle A is 41 degrees. And they want us to find Y and then find X. So let's start with Y. To find Y, we need to notice that Y is the adjacent side to the angle 41 degrees. And then we need another side of the triangle. Well, remember that if R equals 21 here and R equals 21 here, this is also R. So this side here is also 21. And so when I look at the relationship between this angle, this side, and this side, the relationship is tangent, because we know the side opposite angle 41 degrees is 21, and Y is the adjacent side. So we know the tangent of 41 degrees will be equal to the opposite side 21 divided by y. Now to solve for y, what we can do is multiply both sides by y, and we do this to get rid of the fraction. And then we have y times the tangent of 41 degrees is equal to 21. To solve for y at this point, we simply divide both sides by tangent of 41 degrees. And when we do that, we get y is equal to 21 divided by the tangent of 41 degrees. And from there, we plug it into our calculator. And we get 24.1577, etc. And just notice that the other sides here were measured to 2 significant digits, so we should be measuring this also to 2 significant digits. So we'll say y is approximately equal to 24. And this is measured in inches. And now to solve for x, we're going to do a similar type of thing. Notice that x is this line segment right here, and that segment is part of the hypotenuse of this triangle. So we need to notice that the hypotenuse from here to here is x plus 21. Now, this side we know is 21, and we know this angle is 41. So we have an opposite side here, and we have a hypotenuse here, and that relationship is the sine. So we know that sine of 41 degrees is the opposite side, which is 21, divided by the hypotenuse, which is x plus 21. And now to algebraically solve for x, I'm going to multiply both sides by x plus 21. Now when you do that, be sure to use parentheses since you're multiplying by a binomial. These will cancel out. And then on the left-hand side, I'm going to distribute sine of 41 to each one of these. And if I do that, I get x sine of 41 degrees plus 21 sine of 41 degrees is equal to 21. And now I can subtract 21 sine of 41 degrees from both sides. And when we do that, we get x sine of 41 degrees is equal to, now be careful right here, 21 minus 21 sine of 41 is exactly that. 21 minus 21 sine of 41. Some people will make the mistake of trying to subtract these two numbers. Don't do that because you do have a sine of 41 degrees attached here. And finally, we can solve for x by simply dividing both sides by sine of 41 degrees. And when we do that, these cancel out, and we get x is equal to this. And the last step, of course, is to go ahead and plug that into a calculator. And when we do that, we get the value 11.0093, etc. Again, we are only going to take 2 significant digits. So x is approximately equal to 11 inches when we round. So x is approximately 11 inches and y is approximately 24 inches. And for our last example, it says a man is walking away from a 20-foot flagpole. When he reaches point B, the angle to the top of the pole is 60 degrees, and when he reaches point C, the angle to the top of the pole is 50 degrees. Find his distance from the flagpole at point B and at point C. Okay. Now, of course, when you read that problem, you'll have to draw your own flagpole. And the way you do that is you just draw the ground as a horizontal line. You draw your flagpole, which should be perpendicular to the ground, meaning that we have a right angle there. And then now the person is walking away from the pole, and at one point gets to point B, and then gets to point C, and we have these angles going to the top of the pole. So drawing this diagram is a big part of doing this problem. Once you have the diagram, it's not too bad to solve it, because I want you to notice that you have a right triangle here, and x is the distance from point B to the flagpole, so we're going to solve for x. And to do that, we can use trigonometry. So if this angle is 60 degrees, 20 is the opposite side, and this is the adjacent side. And so that means the tangent of the angle 60 degrees is the opposite side 20 divided by x. If we multiply both sides by x, we get x tangent of 60 is equal to 20. And then finally, dividing both sides by the tangent of 60 will give us x. And in this case, x will be 20 divided by the tangent of 60. And then we just need to put that into our calculator. And when we do that, we get 11.5470, etc. Now again, notice that the flagpole is measured to be 20, and the angles are measured to the nearest whole degree. So we're going to go ahead and measure this to be 2 significant digits, which is 11. So x is 11 feet, and that's the answer to the first part of the problem, where they're asking to find its distance from the flagpole at point B. Now we want to find the distance at point C. To find the distance at point C, notice that we need to figure out how big this segment is. I'm going to call this segment Y. Now when I do that, notice that the length of this side of the triangle is x plus y. And now if we look at the larger right triangle, we have an angle 50 degrees, we have an opposite side of 20, and we have an adjacent side of x plus y. So from that, we know that the tangent of 50 degrees is equal to the opposite side 20 divided by x plus y. And in this case, we need to know what is x plus y. So I'm just going to multiply both sides by x plus y. That will cancel these out, and we get x plus y times the tangent of 50 degrees is equal to 20. Now in this case, I'm not going to distribute this because x plus y is actually what I'm looking for, right? Y represents the distance between point B and point C. So x plus y will be the whole distance. So to make a long story short here, if I just divide by tangent of 50, that will give us x plus y is equal to 20 divided by the tangent of 50. And now all we have to do is plug that into our calculator. And when we do that, we get x plus y is equal to 16.78, etc. And again, we're going to round that to 2 significant digits, which will be 17. So the distance between point B and the flagpole is 11 feet. The distance between point C and the flagpole is 17 feet.